All right, so for this section, we're going to be talking about inverse functions. So one of the first things listed in our set of notes here for inverse function is the definition of a one-to-one function. So one-to-one function, essentially in a nutshell, is telling us for every single x value that we plug into a function, we should only get a single unique y value for it. All right, so like we plug in 2 into an equation and we get 5, we shouldn't be able to also plug in a 2 and get like a different number. Right? We shouldn't be getting two different things for the same number that we plug in. Right? I plug in a 1, I get a unique answer. I plug in a 2, I get a unique answer, and so on and so forth. In a visual graphical form, in order to tell if it is a one-to-one function, it must pass the horizontal line test. The horizontal line test states that if you draw a horizontal line clear across that graph and it only intersects at one point and one point only, then it is a one-to-one function. If it crosses at more than one point, then it is not a one-to-one function. Some of the definitions that we're going to be talking about in this section here. So over here, in a nutshell, kind of what this is describing here is we're going to be taking a look at a function, and then we're going to be taking a look at its inverse. So if we have a point on f of x, and we're taking a look at the inverse of that function, think about this point as reversing. The point x, y, so let's just say it was like a 2, -4. When you find the inverse of that, it interchanges, it becomes yx. So if we knew the point 2, -4 was on f of x, what that tells us is that the point -4, 2 would be on our inverse function. So that's going to be something important to note throughout this section here. Otherwise, so I'm going to go ahead and jump into these two examples that we have here before I explain these top notes here. So for these first examples here, it says for f of x is equal to x cubed, find the following. So it wants us just find f of 2. Well, if we're finding f of 2, that means we are plugging 2 into our function here, which is just x cubed. So now we have 2 cubed, and 2 times 2 times 2 is an 8. The second part is asking us to find f inverse of 8. So this is kind of where this definition that I just got done talking about is important. Because if we know a known x and y value for f of x, compare that to what we have here. When we find f of 2, keep in mind that 2 is the x value, and our result here, the 8, represents our y value here. So technically what we're calculating in here is when we plug in a 2 for x, we get an 8 for y. It also visually represents the 0.28 on this function. So if it wants us to find f inverse of 8 here, well, notice we got 8 for our y value here. And if we know that 8 is the y value, 2 has to be the corresponding x value with it. Again, kind of just reverse it. When we plug in a 2, we get an 8. For its inverse, when we plug in that 8, we will get a 2. So our next example says, show that the given functions f and g are inverses of each other. So we're given f of x here. We're given g of x. And the instructions are saying, prove that these two are inverses of each other. Now, in order to prove that two functions are inverses of each other, we have to do compositions here. We have to do f of g of x. We have to do g of f of x. And what we're looking for is we're looking to get x for every single one of these. So it's literally just our compositions. F of g of x should give us an x as our answer. G of f of x should also give us x as our answer. As long as when we do these two compositions, we get an x for both of them, then these two functions are indeed inverses of each other. So let's first figure out f of g of x, which means we're going to take g of x, we're going to plug it in here. So we have 2 minus 3x, where x is going to be a 2 minus x over 3. Now simplify this. When we simplify this, well, let's see. The 3 in the numerator here cancels out with this one, really just leaving us the 2 minus x. Distribute that negative right there, giving us 2 minus 2 plus x. And 2 minus 2 is a 0, which means we did get x when we did this composition, which is good. That's exactly what we're looking for. Now let's do g of f of x. So we're going to do g of x here, so 2 minus x, where x is going to be the 2 minus 3x, putting that over 3. Simplify this. Now when we simplify this, again, distribute in the numerator to get 2 minus 2 plus 3x over that 3. 2 minus 2 is 0, leaving us with the 3x up top over 3 down bottom. Cancel the 3 in the numerator with the denominator, and we also get an x here in the end. Since we got an x for both compositions here, that proves that these two functions are inverses of each other. So essentially, this is one of those problems where the work is what's answering the question. We got an x here, we got an x here. That work, those resulting x's, proves that yes, these are inverses of each other. Our next example, we are given the graph f, and we are asked to sketch f inverse. So if you're given a graph and you're asked to graph its inverse, the first thing that you want to do, find points on f of x, right? This is our f of x, and we need to graph f inverse of x. So sometimes your points will be labeled, sometimes they won't be labeled. So for our example, our points are labeled, right? If it wasn't labeled, you want to go ahead and pick out distinct points from that graph. And what you want to do is you want to take those points and you want to reverse them. So this point here, -3, -4, I'm going to reverse it and say -4, -3. Over here, we have a -1, 2. So we're going to change that to a 2, -1. And then we have a 4, 3. So I'm going to change that to a 3, 4. Because remember, if we have a point x, y on f of x, that becomes yx for its inverse. So take your points, flip-flop their positions. We're going to plot these new points. We have a -4, -3 right over there. We have a 2, -1 there. And then we have a 3, +4. Connect the dots, and that is the graph of your inverse function. So for our first example, we have f of x is equal to 2x plus 3. So finding the inverse of a function is essentially a 4-step process here. Step 1, get rid of the function notation. So remember that f of x is the same thing as y. They represent the exact same thing, just one is function notation, one is not. So f of x is equal to 2x plus 3 is the same thing as y is equal to 2x plus 3. Step 2, interchange x and y. This y becomes x, this x becomes y. Step 3, whereas most of your work is going to come from, solve for y. Get that equation, y equals. Subtract the 3 on either side, giving us x minus 3 is equal to 2y. Divide each side by 2, and y is equal to x minus 3 over 2. Last step, we got rid of the function notation here in the beginning. We need to put that function notation back in. Keep in mind this is now the inverse function that we found. So we're going to replace y with the inverse function notation here. And the inverse is equal to x minus 3 over 2. So that is our function there. It also wants us to find the domain and range. So if you take a look at the domain and range of this function here, this is a rational function. The only thing that tends to throw the domain off of a rational function is when the denominator is equal to 0. But keep in mind this denominator is a 2, right? So there is literally, if there's no x, if there's no variable in the denominator, there's nothing that's going to make that equal 0. There's no way to magically turn a 2 into a 0. So our domain is a negative infinity to a positive infinity. To maybe easily or more easily see the range here, keep in mind that the function that we're actually working with here, yes, it's in rational function form, but this is really just 1/2 x minus 3/2, right? When we take everything in the numerator and put it over the same denominator, that's all this function is. This is a linear equation. And a linear equation has the domain and range of a negative infinity to a positive infinity. So this is our function itself, our domain and range. I'm going to skip the second example here. You can work that one on your own to test yourself here. I am going to do this example here at the bottom. So let's go ahead and find the inverse of this function. Step 1, replace f of x with y. Step 2, interchange x and y. So this y becomes x. These two x's here become y. Step 3, solve for y. So since I have a division over here on the right-hand side, I'm going to undo that division by multiplying each side by y plus 1. So that this denominator cancels with this. I can drop down that y plus 2. On the left-hand side, actually multiply this out. X times y is xy, plus x times 1 is an x. Now the whole point here is to solve for y. So what I need to do is I need to get everything that has a y on each side, everything else on the other side. So I'm going to subtract this y to the left so that I have xy minus y on the left. And then I took this x and subtracted it to the right-hand side to where I now have a 2 minus x there on the right-hand side. So I'm just going to rewrite that here so I have a little bit more room to write here. We are solving for y, so our next step here is going to be to factor out that y from the left-hand side. Again, we have a y as our GCF. Pull it out to get x minus 1 is equal to that 2 minus x. Divide out by that x minus 1 on each side, and y is equal to 2 minus x over x minus 1. Plug in that inverse function notation. Oh, I'm sorry, I just wrote that wrong there. Plug in that inverse function notation. F inverse x is equal to 2 minus x over x minus 1 as our function here. Now the domain and range of this. The domain and range of a rational function, take the denominator, set it equal to 0, and solve. Your domain is everything except for that. That means our domain is everything except for a 1, right? Literally everything else except for that number 1 there. In order to find the range, you are essentially looking for, are there any horizontal asymptotes? Now, in order to determine that, you need to take a look at the degree of your function here, or more specifically, the degree of the numerator, the degree of the denominator. So we need to take a look at the degree of the numerator. And in the numerator, our degree is a 1. In the denominator, our degree is also a 1. So when that happens, you want to look at the leading coefficients in front of them. So in front of this x, we have a negative 1. In front of this x, we have a positive 1. So that just tells us negative 1 over 1 is a negative 1, right? Which means we do have a horizontal asymptote at negative 1, which does break up our range at that point. So that means our range is negative infinity to negative 1, union negative 1 to positive infinity. The last example that we're going to talk about here is the average rate of change of F inverse. So the formula for average rate of change is f of b minus f of a over b minus a. So it makes sense that the formula for the inverse is kind of almost like the opposite. If you flip it, if you take the reciprocal of it, notice we have b minus a over f of b minus f of a as our formula here. So taking a look at our example, we're given what f of x is, but we're told that f of 1 is equal to negative 1. So remember that this 1 is our x value, the negative 1 is our y value. We also have a secondary x value, right? So let's call this x1. This is x2. When we plug in this x, we get this y. When we plug in this x, we get that y. So when we plug that in here, so b minus a, so think of that as x2 minus x1. That's going to be a 3 minus a negative 1. I'm sorry, a 3 minus a 1 is what we have here, right? A 3 minus the 1. I'm sorry about that. Over f of b, right? So if we plug in a 3, which is our b, we get a 1/3. So f of b is the 1/3, and we're going to subtract that to a negative 1 there. So when we simplify this, 3 minus 1 is simply a 2. Double negative rule down here makes this to 1/3 plus a 1, which is really just 4/3. If we add that together, right, 1 plus a third is 4/3. when we do this division, 2 divided by 4/3, again, divide that by hand, throw that in your calculator, we do end up with a 3/2 there as our average rate of change of this inverse function.